So we've seen now how the magic equation for tricolorability gives us a computational tool for determining whether a given knot has a tricoloration. And if it does have a tricoloration, how many tricolorations does it have? This seems like it could be a really powerful way to distinguish between different types of knots. The limitation that it has, though, is that it only uses 3 colors. And tricoloration might not be enough to distinguish between knots in general. We may need to use 4 colors, or 5, or 7, or 12, or 18, or 212, right? What we'd like to do is push the envelope a little bit and figure out how to go from a tricolorability condition into a k-colorability condition. If I have k colors to work with, how do I come up with a new magic equation which I can then use to build a square system of linear equations that I can then use modular arithmetic to determine whether or not solutions exist for that k-coloration system of equations. This is going to be ultimately the most complete invariant for a knot that we can build, is somehow going to be a way for us to combine all of those different k-colorabilities into one higher algebraic structure. That's where we're ultimately going. And so the first step we need to figure out is how to go from 3 colorations magic equation to a k-coloration magic equation. So the first thing that's legitimate for us to worry about is we might lose the pretty form of the magic equation that we had for tricolorability. X plus Y plus Z is congruent to 0 mod 3. That seems like a really friendly equation to work with, and it makes the linear algebra pretty nice. So what's going to happen if we try to go from 3 to more than 3 colors? Are we going to lose that magic equation? So one of the ways to think about how this magic equation works is we're going to think about it now as a tool for determining the color that a third arc must be if we know what the colors of 2 of the other arcs at its crossing are. So what I'll do is I'll solve this magic equation for Z, just subtract X and Y from both sides. Remember, this is arithmetic modulo 3 still. And since it's arithmetic modulo 3, I can take one of these -1 coefficients in front of either X or Y, and I can replace it with 2. Just conventionally, we like to have one of them be 2 and the other one be -1. This is, if you look at a lot of classical results about knot theory, this is how they think about the magic equation. That if you tell me what colors the arcs X and Y are, then I'll use this equation to then compute the color that the arc Z has to be. And it's still the magic equation, which means that if X and Y have the same color, then Z is necessarily going to be the same as X and Y. Where if X and Y have different colors, then Z is going to be a different color still from what X and Y were. Right, so it's still the same magic equation, it's just rearranged in the way that you're going to see it if you look at some more classical references on knot theory. So how we can take this from tricoloration to k-coloration, for k greater than 3, is we're going to take the coefficients and change the coefficients in this equation. And we're also going to change the modulus with respect to which we do the arithmetic. Right, so before we had mod 3 arithmetic because we had 3 colors to work with. Now we want mod k arithmetic because we're going to have k colors in our crayon box. But we still want this equation to have the property where this equation is true every time all of the colors at a crossing are the same, and false anytime all of the colors at that crossing are not either all the same or all different. Right? So how do we push that envelope? Well, what we'll do is we'll take the -1 coefficient that we see here in front of the x, and we're going to replace it with a new parameter that we're going to call t. We'll see in a minute what properties t has to have, but we're just going to call it t for the moment. And if I choose this coefficient to be t, then what does the coefficient of y end up needing to be? It turns out the choice we want to make is 1 minus t, and it's a little mysterious right now why this is the right combination of choices to make. So what I want to do next is look at why this particular equation is the right equation to use, because it's going to have that same magic property that our magic equation for tricolorability had. So why was this the right choice? Let's ask the question, is this equation still a magic equation? If I choose an x and a y, however I like, right, choose a color for the arcs x and y, I'm going to think of x and y as being my undercrossings here. If I choose the colors of the undercrossings, and I then determine the color of the overcrossing using this new equation, will this new equation be true if and only if we either have all 3 being the same or we have all 3 being different at this crossing? So the question, the way I'm going to frame that question is, if 2 of the colors in this diagram agree, then what does that tell us about the third? So there are three cases, and I'm going to, for now, just be ignorant of the fact that there may be some symmetry involved in this equation. And think of the three cases as being, if I choose x and y, my two undercrossings, to have the same color, versus x and z, one of my over and one of my unders, and y and z, my over and the other under crossing. And if two of those are the same, then what does that tell us about the third? Well, we'll just use the equation, z equals tx plus 1 minus ty, and solve it for each of the three, x, y, and z, right? So in the case where x and y are the same, then z is going to be tx plus 1 minus ty, and then we're going to use the fact that x is equal to y in a second. And then likewise for these other two. But the first thing that we notice about the equations for y, solved for y, and solved for x, is that they require us to divide. The equation where we solve for y requires us to divide by 1 minus t. The equation solved for x requires us to divide by t. And since we're working in modular arithmetic, we need to make sure that those divisions are actually possible. You'll remember from number theory that these divisions are only possible when t has a multiplicative inverse inside of our number system, which is not a guarantee when we're working with modular arithmetic. And so the way to guarantee that we have a multiplicative inverse and so we can actually solve these equations is to require that t be what's called a multiplicative unit. And in number theory, t is a multiplicative unit mod k if and only if t and k are co-prime, if they have no interesting common factors, if the greatest common divisor between k and t is equal to 1. So that's actually the only condition that we're going to put on our t for this equation. We're going to say as long as t is co-prime to k, then this is still going to be the form of what we'd like for to be our magic equation for k-colorability. And so if we then assume that that's true, then what do these equations tell us about the nature of the third color when the first two colors at one of my crossings are equal? Well, if x is equal to y in the first case, then that means that z is tx plus 1 minus t times x. If x is equal to z in the second case, y is going to be z minus tz over 1 minus t. In the third case, where y is equal to z, then x is equal to z minus 1 minus tz, all over t. And now all we have to do is the arithmetic to simplify out the right-hand sides of these equations and find out that when x is equal to y, z must be equal to x. And when x is equal to z, y must be equal to z. And when y is equal to z, x must be equal to z. And each of these computations is also reversible. So what we find out is that any time two of the colors at a crossing happen to agree with one another, the third must also agree with the first two. And so it turns out this equation, this new generalized equation, is still magic in the way we need to be magic to determine whether a k-coloration, a proposed k-coloration of a knot, is or is not actually a valid k-coloration. This magic equation is true at every crossing if and only if we have a valid k-coloration of our knot. And this is going to reduce back down into our tri-coloration condition if we choose k to be 3 and if we choose t to be 2. But now if we make different choices of k for different numbers of colors and different choices of t as the thing that we're going to divide by in my magic equation, as long as it's co-prime to k, we'll get a valid way of doing algebra with it. Then we're going to be in great shape, and we have a new generalized magic equation that we're going to be able to use to determine the k-colorability of knots. So we've lost one magic equation, but we've gained a new, more powerful, generalized magic equation. And this is really, really great news. Let's see if we can put it into practice to distinguish between two knots using the same linear algebra that we use for tricoloration. So here are two knot diagrams. And these diagrams were taken from a blog post by David Austin at Grand Valley State University. Here are two knot diagrams. One of them is an 8-crossing diagram. The other one is a 10-crossing diagram. But it's not immediately obvious whether these two diagrams represent the same knot or whether they represent different knots. And that's ultimately the question of knot theory, is how do we use the tools at our disposal to determine whether two diagrams are showing us the same knot or not. So let's use the generalized k-coloration idea to see if we can distinguish between these two knots. Because if these two knots are in fact the same knot, then that must mean that any type of coloration that I choose is going to give me the same results for both of these knots. But if I can find even a single disagreement, a single choice of number of colors, or of the value of t that I use in my magic equation, that gives me different results for these two knots, then we must know that these two knots are different. So let's try some stuff. Let's first start with the kind of coloration that we've had some experience with. What if we just do honest tri-coloration, k equals 3, t equals 2? If we do that, we find out that the knot on the left, my 8 crossing knot, ends up with a single free variable, and the 10 crossing knot on the right also ends up with a single free variable. So, spare you the details, you can reproduce them if you like, use some technology, but it turns out that we can't distinguish between these two knots using tri-colorability, because it turns out that each of these knots only has the trivial tri-coloration. In other words, we take a single color and we color all of the arcs the same color. That's not really a tri-coloration. So tri-colorability is not sufficient to distinguish between these two knots. So might some higher colorability be able to do it for us? Let's choose 5 colors instead of 3. So the question is, can we 5 color this pair of knot diagrams in essentially different ways from one another? If we can, then these two must represent different knots. So our new magic equation, if we choose k equals 5 and t equals, we can choose whatever we want for t, remember, as long as t is an inverse mod 5, so as long as t is co-prime to 5. So let's just pick out of a hat. Let's choose t equals 4. Okay, 5 and 4 are co-prime, so we can actually get a valid magic equation for t equals 5, k equals 5, t equals 4. Okay. And the magic equation looks like this. Z equals 4x plus 1 minus 4y, and the arithmetic is done mod 5. If I simplify that, that's 4x minus 3y. And since negative 3 is the same as positive 2, mod 5, I could also think of it as 4x plus 2y. So if you tell me the colors of two under arcs, x and y, then I can tell you the color of the over arc by taking 4x plus 2y computed mod 5. And that's going to give me the color of the over arc. Or we could also rewrite that 4 as a negative 1. So it turns out that this looks exactly the same in form to our original tri-colorability classic magic equation. But it still has all the same properties that we want, right? If I choose 2 colors, this equation is going to determine the third one for me. Okay, so it means that each of the linear equations that are going to build my system are all going to look the same. It's all going to look like x minus 2y plus z is congruent to 0, mod 5. So each one of the rows in my matrix is going to have a 1, a negative 2, and a 1, and where those appear depend on which arcs are incident at that crossing. We could also, instead of a negative 2, think of this as being a 3. So when I write down the system for each of these knots, I'm going to get a bunch of rows that have a pair of 1s and a 3. And the way that I drew the diagram a second ago, we're actually going to think of y as being my overstrand here, and x and z as my understrand. So the overstrand is going to get the 3 coefficient, and the understrands are going to get 1 and 1. And so using that idea, we can transform each of these knot diagrams into a square system of linear equations mod 5 that will determine how many 5 colorations exist for that knot. So that's going to require us to label all the arcs in this diagram. So I'm going to label all 8 of my arcs in the knot on the left here, 1 through 8. And when I do that process, I want to know how many free variables exist for that system of equations. So let's use technology once again to, once we build this system, figure out what its row echelon form is. So after I do all of the work on the knot diagram's labeled arcs to figure out how the magic equation looks at each one of the 8 crossings, I get a square system that looks like this. The pair of 1s then represented by under crossings, and 3 represented by overstrand. And so that gives me this 8 by 8 matrix. And if I find its row echelon form with the linear algebra being done over the integers mod 5, so I'm using Sage once again here to do this calculation. If I find the row echelon form, this is what it looks like. Okay. And the most important feature of the row echelon form is how many free variables exist. And a free variable is just going to correspond to a column in this row echelon form which doesn't have a pivot. And if I look down the diagonal, I have pivots in every column of 1 through 7, but I don't have a pivot in column 8. So we have one free variable for this particular system. And colorability-wise, that means that we only have that trivial solution. As soon as I choose the value of the coloration of this one arc, arc number 8, as soon as I decide how to color that arc, it determines for me how to color all the other arcs in the diagram. And so we only have that trivial way of coloring all the arcs the same from my box of 5 crayons. So 5 coloration is not very interesting for the knot diagram on the left. What about the knot diagram on the right? So this diagram has 10 arcs, so we're going to label them from 1 through 10. And let's do the linear algebra to figure out how many solutions, how many 5 colorations exist for my 10 crossing knot. So running through my knot diagram, I end up now with a 10 by 10 system of linear equations that I want to satisfy if I have a 5 coloration of my 10 crossing knot. It looks like this. I can use, again, Sage to find the row echelon form for this matrix where all the arithmetic is being done over the integers mod 5. And the row echelon form for this ends up having a pivot in columns 1 through 8, but column 9 and column 10 both correspond to free variables, no pivots in those two columns. So we end up with 2 free variables in the case for the knot diagram, my 10 crossing knot diagram over on the right. So what does that mean about 5 colorability? It means that there are 2 independent choices of how I color arcs. Arc number 9 and arc number 10. Maybe that's this one and this one. But as soon as I decide how to color arc number 9 and arc number 10, I can make those 2 choices independently. And because I can make those 2 choices independently of one another, and they jointly determine the colors of the other 8 arcs, I now have more freedom in how to use potentially 5 colors to color these. And since the choice is independent, I can color those 2 arcs differently from one another. Because I can color those arcs differently from one another, that must imply that there exists a non-trivial 5 coloration. We don't know still whether it uses all 5 colors or not, but we know that there exists a non-trivial 5 coloration for the knot diagram over here on the right. And if we wanted to do the combinatorics of how many 5 colorations exist, since there were 2 free variables, and we can choose each one of those free variables from among 5 choices of colors in my crayon box, 0, 1, 2, 3, and 4, that means that I have 5 times 5, 5 squared, 25 potentially different 5 colorings for this knot. 5 of those are still going to be trivial. If I color 2 of those arcs to be the same, then all 10 of these arcs are going to end up being the same. And so we throw away the 5 trivial colorations. There are 20 non-trivial colorations with 5 crayons for this particular knot diagram. Some of them might use only 3 of the 5. We don't know. But since we already determined tri-colorability was out, actually that's not the case. Maybe some of them use 4 colors. The rest of them might use 5 colors. But we know that non-trivial 5 colorations exist for the knot on the right, where non-trivial 5 colorations do not exist for the knot on the left. And so here we've used 5 coloration to distinguish between these 2 different knots. And that's super powerful. You might imagine that we could keep iterating this process until we find a disagreement, perhaps, and that might be an efficient algorithm for determining whether 2 knots are or not, in fact, the same. The only question we don't know yet is whether we're guaranteed to always find a disagreement when 2 knots are different. Or might we look forever, find that they all agree, and yet still have 2 different knots? So does coloration give us a complete invariant if we're allowed to consider all the possibilities for different colorations? Or might there still be some play out there of 2 different knots that have all the same colorability properties? What we want to do is we want to get to building a new algebraic structure, a new type of algebraic structure that can encode all of the colorability properties for a knot. And if we can do that, it turns out that what we get actually is the holy grail complete invariant for knots. To get there, though, we're going to take a short detour and think about how coloration works for rational tangles to sort of tie up some of the loose ends, pun possibly intended, from the earlier part of the semester, so that we can then focus on getting to that higher algebraic structure.